Good morning, students. We are going to review class exercise 1 of topic 18, carboxylic acids and its derivatives. So for the first question, you are supposed to rank the compounds below in order of increasing acid strength. Okay, so let's try to take a look at what are these compounds. So from the functional group presence, you notice that they are all carboxylic acids. Okay, so basically the generic form of carboxylic acid looks something like this. Okay, and you know that it partially ionized to give you the carboxylate anions and H plus. So usually the benchmark we are looking at will be ethanoic acid, which has a pKa of about 4.8 to 5. Okay, so why is it that the carboxylic acid tends to be acidic? That's because if you take a look at the conjugate base, okay, over here, you'll notice that let's do a bit of revisions. So this is the pi bond. Okay, this is the pi bond which have the side-on overlapped, and then this is the carboxylate. This is the O minus. Next to the CO pi system, you notice that the lone pairs of electrons can partially, or it can delocalize across the CO pi system. And because the carboxylate anion is symmetrical, we normally say that the negative charge delocalize equally between the two oxygen, or it is distributed equally between the two oxygen. So in essence, each of the oxygen will take on a negative half charge. Yeah. So because of this stabilization, we are confident, or we are aware that the carboxylate anion is stabilized through resonance. Normally we say that the delocalization of the lone pairs of electrons of the O minus across a CO pi system, this delocalization we tend to sometimes coin the term resonance to describe it. Okay, so that's a little bit of a revision. Why is the carboxylate anion stabilized? Then now, back to the question, right? So we are aware that the carboxylate anions is stabilized. Then right now we are supposed to rank 3 carboxylic acids over here. So what is the key factor we need to consider when we are discussing which carboxylic acid is more or less acidic? Okay, so for all the 3 acids given to us, right, the main issues or the main idea we need to discuss, right, is not so much about the stability of the carboxylate anion, which means it's not so much about the stability of this carboxylate anion, but rather it is how this carboxylate anion is further stabilized. So what kind of factor will lead to its further stabilization? Okay, so with that, we take a look at all our examples. Okay, so from our examples, we notice that for the first example, we have a floral group at the second carbon. And for the third example, we notice that there is a floral group at the third carbon. So this is, so the carboxylate acid, it's labeled as carbon number 1, and then this is 2 and 3. Okay, so this is 1, 2, 3. Okay, so between 2 fluoropropanoic acid, right, the floral group is at the second position. So that means that if it's going to ionize to the carboxylate anion, right, versus the third one, you will notice that the floral group is closer to the carboxylate anion for 2 fluoropropanoic acids, for the conjugate base of 2 fluoropropanoic acid as compared to the conjugate base of 3 fluoropropanoic acid. So that means that this is stabilized more as compared to this via the electron withdrawing inductive effects of the floral group. Okay, so the floral group purely exerts an electron withdrawing inductive effect through the sigma bonding framework, and it helps to further disperse the negative charge of the carboxylate anion. You notice the way the answer is being phrased. Yeah, so the idea here is not so much about the stability of the carboxylate anion. Yeah, the idea here is about how the negative charge, okay, over at the carboxylate anion is further dispersed by the presence of the inductively withdrawing group. And because the floral group for 2-fluoropropanoic acid is at the second position, whereas that of 3-fluoropropanoic acid is at the third position, so being closer to the carboxylate anion, right, will help to further disperse the negative charge of 2-fluoropropanoids as compared to 3-fluoropropanoids. And of course, over here, right, we don't really need to discuss propanoic acid because propanoic acid is similar to ethanoic acid. The carboxylate anion, in this case, there is no further stabilization of it due to any of the electron withdrawing atoms or groups. Yeah, so we will reframe our discussion from it. So basically, for our discussion, right, we will just discuss why is it that 2-fluoropropanoic acid and 3-fluoropropanoic acid are more acidic as compared to propanoic acid. Yeah, so in that case, the benchmark is therefore propanoic acid. Yeah, so if we're going to arrange them in order of increasing carboxylic acid strength, that will be first we have propanoic acids, followed by 3-fluoropropanoic acids. Okay, and this is followed by 2-fluoropropanoic acids. Okay, and I have already explained why they are being placed in that order. So most importantly, when we are trying to discuss strength of acids, a very good practice is to group all of them in the same category together. So in this case, all carboxylic acids, we group them together. If you are supposed to compare between carboxylic acids and phenol, then we group all the phenols together, all the carboxylic acids together, and we compare them separately. And then after that, we discuss why carboxylic acids are stronger acids than phenol. I think it has been discussed in some of that class exercises. Okay, yeah. Then question 2, outline the reaction scheme for each of the synthesis below. So this is a synthesis question. Okay, so often get them occasionally in assessment. So for synthesis questions, what exactly are we looking at? Okay, so over here, right, you're supposed to clearly indicate the reagents and conditions for each steps in your reaction scheme, show the structures of all intermediates. Okay, so if you take a look at what we have, right? Okay, so maybe I'll show you in skeletal. So we have 2-bromo, or rather bromoethane, and then I'm going to get this particular ester. Okay. Yep. So I'm going to convert a bromoalkane, or in this case bromoethane, into an ester. So if you count the total number of carbon, this is 1, 2. So I suppose this should be 1, this should be 2, and this should be 3, right? Okay. So how am I going to form the ester? I think that is the question that we often will ask, and because this is a topic on carboxylic acid derivatives, right? So to form the esters, normally what do we need? We need a carboxylic acid. Okay, we need a carboxylic acid, and to get the ester, the general procedure is to use corn sulfuric acid as the catalyst, and we use methanol in this case. Okay, so I'm just going to write them out. Corn H2SO4, okay, in catalytic amounts. Okay, and then CEH3OH, that's methanol, and then we're supposed to heat under reflux, okay, in order to ensure that I get the ester in appreciable yield. Okay, then after that, what's going to happen is that how am I going to convert bromoethane into the carboxylic acid, taking into consideration that the number of carbon remains as 2 . Yeah, so some of us might be thinking, hey, we add a cyanide and then we hydrolyze. But if you add a cyanide, you are increasing the number of carbons from 2 to 3, so that is not a good strategy. Okay, yeah. So in this case, I'll just simply perform a nucleophilic substitution, because in order to get a carboxylic acid, I think what's going to happen is I will need an alcohol. Okay, so that the alcohol can be oxidized into the carboxylic acid. Yeah, and then of course for nucleophilic substitution, we are just going to use sodium hydroxide aqueous, and then we heat it. Yeah, so this is simply nucleophilic substitution, and then from the alcohol to the carboxylic acids, we are just going to use KMnO4, acidify with H2SO4, and then heat. And then the primary alcohol, will be oxidized to a carboxylic acid. Yeah, some of us might be wondering, can we instead of using this, can we convert this to an acyl chloride? Yes, we can do that if you want, but that will take up a little bit more steps lah. Yeah, so if you prefer to convert this to an acyl chloride, you can just use PCl5, and then from the acyl chloride to the esters, you simply just need to add methanol. Yeah, you do not need to add consulfuric acid. Yeah, so whatever steps you take, right, you need to ensure that you are confident of the reagents and conditions used. Okay, so if you cannot really remember, then I suggest we should always stick with the simplest strategy. Okay, then for part B, I'm just going to sketch out the skeletal. Okay, so we're going to have something like this, and then a CH and an OH. Okay, this is a starting material, so propane 2-ol. Okay, and then after that, I'm going to end up with something like this and a carboxylic acids. Okay, yeah, this shouldn't be too difficult, because at the end of the day, right, you'll notice that the number of carbon increases by 1. Okay, and then I think all of us are quite familiar that in order to increase the carbon by 1, one of the key strategy is to add a cyanide. Okay, so of course, before the cyanide can become the carboxylic acid, you need to hydrolyze it. So normally the hydrolysis, you just use a mineral acids and then heat. Okay, and then the byproduct is ammonium in this case. And then how do we introduce the cyanides? It's through nucleophilic substitution. So in this case, maybe a Br here. So in order to perform nucleophilic substitution, we probably need ethanolic KCN heat. Okay, and then we need to convert the OH to the Br. How do we do that? Again, the usual strategies, we will just use PBr5. Okay, or thionyl bromides. Okay, you can use thionyl bromide if you want, SOBr2. Okay, so that should work perfectly. Okay, yep. And then going to move on to question 3. Question 3 supposed to suggest one simple chemical method to distinguish between the following pairs of compounds. So this distinguishing test. Question 3 tests us on to be able to distinguish one compound from the other. State what you observed. Okay, so clearly this is phenol. This is benzoic acids. Okay, so we have phenol, we have benzoic acids. Okay, how do we distinguish them? The most clear-cut one I can think of will be use a neutral iron 3 chloride. Okay, because for neutral iron 3 chloride, right, phenol gives me a very characteristic color, which is what we call purple coloration. Okay, purple coloration occurs. Okay, so the solution will turn purple and the purple is quite intense. Okay, so then for benzoic acid, no purple coloration. Okay, then of course, if we want to focus on this key ingredient, which is the carboxylic acid, right, then we can use sodium carbonate aqueous. Okay, so for benzoic acid, we will have effervescence of colorless, odorless gas that gives white PPT in lime water. Okay, then for phenol, no effervescence. Okay, so you can use either of them. Because question is you're supposed to only use one. I gave 2 so that just to impress upon you that if I were you, I would choose the simplest one. Of course, I would choose neutral iron 3 chloride. But if let's say at that point in time you can't think of it, then of course sodium carbonate aqueous works wonderfully as well. Okay, so there are many answers, several answers you can think of lah. So do not worry about that you can't think of the right one during assessment. But most importantly, right, I thought I need to stress this. It must be a simple chemical test. The key word here is simple, meaning you can do that within 30 seconds to 60 seconds. Test tube chemistry preferably. Any warming will be done in a water bath. No direct heating, no reflux, no complicated setup. Okay, then methanoic acids. What about methanoic acids? Methanoic acids and ethanoic acids. Yeah, so what can we do for what can we do to distinguish between both of them? Of course, one way we can do, right, is you know that for methanol acid, one end of it, it contains the activated CH due to the carbonyl group. Yeah. So what we can do is we can introduce KMnO4 with sulfuric acid heat. Okay, of course heat in a water bath lah. Yeah. So I'm going to expect effervescence again of colorless, odorless gas. Okay, that gives white PPT in lime water. Okay, same as this. Okay, then for the case of ethanoic acid, no effervescence of blah blah colors, odorless gas. Yeah, so that is something that you need to be aware of, and it's like a special case, because for methanoic acids, the aldehydic CH is activated, so it can be oxidized further to give you carbonic acid, and carbonic acid will decompose to give you CO2. Yeah. Okay, then of course we emphasize on the aldehydic groups, right? So that means that this particular group can also undergo positive test in Tollens. If you want, you can do the silver mirrors test. Okay, so if you want, you can put Tollens reagents, then this will give you silver mirror. Then for ethanoic acid, no silver mirror. Okay, yeah. Then we'll move on to question 4. Question 4 is a little bit interesting. So lithium aluminum hydride and another complex hydride, sodium boron hydride, are useful reducing agents. So lithium aluminum hydride is more powerful. Okay, if you look at H, you can try to calculate the degree of unsaturation. Okay, 2n plus 2. So it's minus 4 divided by 2. So degree of unsaturation of 2. K will be 0. Okay, J will be 1. Okay, so you notice that for the case of H, it become a saturated compound, which is K, in the presence, or rather when it's being reduced by lithium aluminum hydride in dry ether. But for sodium boron hydride, in the case of H, right, it gets reduced, yeah, but the degree of unsaturation reduces just from 2 to 1, so it's not saturated. So one part of it is still saturated. Okay, and then they give you a little bit of clue about H, J, and K. They mention that all the compounds give yellow PPT with aqueous alkaline iodine. So you know that all the 3 compounds, right, they might share a similar moiety, either the methyl ketone, okay, or the methyl alcohol. Okay, which makes perfect sense. Because if you reduce a methyl ketone, right, you will get a methyl alcohol, and then both of them will give you positive iodoform test. So you can be extremely confident that H contains this. Yeah, you can be very confident that H contains this, and you can also be confident that J and K probably contains this lah. Yeah, in order for you to get the iodoform test. Yeah, that is something that you need to be aware of. Okay, and then all 3 reacts with sodium metal. Okay, so for sodium metal, right, this is not a very useful information, because basically they react with protonic hydrogens. Yeah, so they are trying to tell you that, okay, H, in addition to containing this methyl ketone moiety, right, it also contains a protonic hydrogen. Of course, if you try to do a bit of math here, so H is C3H4O3, right? We'll subtract off COCH3, so that's 2C, 3 H's and 1 O, right? You end up with CHO2. So essentially this is carboxylic acids. Okay, so you know that R in this case for H is a carboxylic acid. So straight away we can find out what H is already. So H will look like this. Okay, so this is H. And we are familiar that that K is saturated, right? K is saturated. So therefore, right, from H to K, lithium aluminum hydride, not only reduced the methyl ketone to methyl alcohol, okay, but it also reduced the carboxylic acids to a primary alcohol. Yeah, so that's 3 carbons here, and then 2 O's, and then 3, 4, 5, 6, 7, 8, 8 hydrogen, which fits the formula C3H8O2. Okay, and of course, based on this, we know that for sodium boron hydride, it's only able to reduce, so that's J, right? Yeah, so it's able to reduce the ketone, the methyl ketone to the methyl alcohol. Okay, we can be confident about that as well, because that's something we learn for lectures, right? But the carboxylic acid remains, and that explains why J has 1 extra degree of unsaturation, and the number of oxygen remains as 3 here. Okay, and of course, all the 3 gives reactions with sodium metal because of the presence of the protonic hydrogens. Okay, so that makes perfect sense. Okay, I think we have looked all the information. Oh, okay, so there's one further piece of information which we didn't discuss, but fortunately or unfortunately, we have already solved it. H and J reacts with sodium carbonate, but K does not. So H and J reacts with sodium carbonate, but K does not. So that means that K no longer have the carboxylic acid, which makes perfect sense now. And then H and J contains the carboxylic acid, which explain why they will react with sodium carbonate. Alright, so this is one of the A-level questions. I think we are done with reviewing it. So I hope this particular class exercise isn't too challenging for most, if not all of you. Thank you very much.